Hi, so this video will be dedicated to walking you through the solution of an advanced IMO problem, International Math Olympiad problem. And it'll also equip you with some useful techniques for when you want to solve such advanced problems or when you ever encounter such ones. So this specific problem appeared in an actual International Math Olympiad competition, and it states that let A, B, and C be real numbers such that the quantity BC minus A squared to the power of -1 plus the quantity CA minus B squared to the power of -1 plus the quantity AB minus C squared to the power of -1 is equal to 0. If this statement is true, it is asking us to show that, or to prove that A times that same quantity in the first term, instead now to the power of -2, plus B times the same quantity to the power of -2 plus C times the same quantity to the power of -2 is equal to 0. Now, when you're first looking at this problem, it might seem a bit daunting because there are many what you might want to call hairy terms, and it doesn't seem like there's any immediate approach. And so what I'm going to do now is walk through a solution for this problem that does in fact end at this result. And throughout the actual solution, you'll find that there's many useful techniques that you'll learn that'll help you a lot of other problems, both similar and not similar to this problem. So to start off the solution, the first thing we're going to want to look at is these terms that are all to the power of -1 in the given in this initial statement right here. So what we might want to do is take each of these statements, or each of these terms, and substitute them for a certain variable, say x, y, or z. So I'll do that right now. I'll say x is equal to this first term, not to the power of -1, just this first term. So we have x is equal to bc minus a squared. Then we can say y is equal to the second term. Y is equal to ca minus b squared. And then we have z is equal to ab minus c squared. At this point, we can rewrite the given with these new substitutions as 1 over x plus 1 over y plus 1 over z is equal to 0. And we can say this simply just because of the substitution, and we know that anything to the power of -1 is simply equal to 1 divided by that quantity. From here, we now realize we can rewrite what we're looking for using the same substitutions as a over x squared plus b over y squared plus c over z squared is equal to 0. This is what we're trying to prove. Now, the next step is a step that is not taken by many problem solvers that is actually very critical to solving this problem. And this step may seem reckless at first, and it is, but it will definitely pay off once you realize what it actually does. And this step is essentially multiplying this trinomial by some trinomial, another trinomial term that'll result in producing these three terms along with another set of cross terms. Is going to have to be a over x plus b over y plus c over z is equal to 0. And we know that this is equal to 0 because we know that this term is equal to 0, and anything multiplied by 0 is 0. And so if you see, this will in fact produce these terms because you have 1 over x times a over x will produce a over x squared. 1 over y times b over y will produce b over y squared, and 1 over z times c over z will produce c over z squared, along with the other cross terms that result in multiplying trinomials. So if we want to actually expand this, which we should do, we will get that, and I'll write 0 over here just on the side. We'll get that if you want to just expand these first terms right here, we get a over x squared. Now 1 over y times b over y, like I said before, will give you b over y squared, plus 1 over z times c over z will give you c over z squared. And this we notice that we have these same terms that we want, which is a over x squared plus b over y squared plus c over z squared. And we can also add these like terms that we have with like denominators, and we can also multiply by a common denominator, or to get a common denominator of x, y, z, we can multiply each term by the single term in the bottom that it doesn't have. And what I mean by this is that if we have b over xy plus a over xy, both of these terms don't have a z at the bottom, so we can multiply z at the top to get a common denominator of x, y, z. Do the same process for each of these with the term it doesn't have in its denominator, and what we're going to result with going to show that this is in fact true, or this is in fact true, both of these statements are synonymous, we must prove that this numerator is equal to 0. Because if this numerator is 0, we know that this also must be 0, which proves what we'd like to prove. So let's now make the substitutions back that we have for x, y, and z, and see what we get. So this term right here, the numerator, I'm going to expand as a plus b times z, and z is equal to ab minus c squared, plus a plus c times y, which is ac minus b squared, or ca minus a squared, they're synonymous. And then we have plus b plus c times x, which is bc minus a squared. And that's equal to this term. Now if we'd like to expand this, we get a squared b plus ab squared. And this is just using what you might know as the FOIL method, but it's essentially just a way of using the distributive property with multiple things to distribute. Might strike you, and it shows you that each of these terms has a negative also existing in this expanded version of these binomials. And so if you want to actually see what I mean by this, we have a squared plus b here, and we have a squared negative a squared times b here. So a squared times b, negative a squared times b. These two which means this is equal to 0. And the aha moment here that we have found is that if this massive term equals 0, that means this term right here is equal to 0. And if this term right here is equal to 0, that means this whole fraction is equal to 0. And if this whole fraction is equal to 0, and we know that this entire expression is equal to 0, that means this also must equal 0. And at the very beginning, we made a substitution that told us that this is actually in fact equal to this, just based off our substitution here and based off the properties of exponents at the very top. So at this point, you'll realize that we've now fundamentally proven that this statement must be true given that this statement is true for any real values of any given c.